hear that, right?
No.
If you hear that? I know I've got bad hearing, but, okay. Let me try one more time to see if I can get speakers on this thing to actually do something. Because I'd have to go through that.
Professor, what does she divide to get that
Oh.
answer?
So looking at the formula, speed is equal to frequency times the wavelength. The speed of sound, 340 meters per second, is equal to my frequency times the wavelength, which we calculated to be 1.66 meters. So the math problem we're dealing with is 340 is equal to 1.66 times the frequency. That's the math problem. So she divided both sides by 1.66,
And that's how she got the answer.
and that's how she got 204.8.
Okay.
Oh, okay, wait a second. Yeah, you can hear that, right?
Did you want to use one of our phones? Because I was able to get it pulled up.
Yes, thank you. I can't tell my wife about this because then she'll say, well, if you get a decent phone, no chance she's gonna watch this video, so. All right, that's 440 hertz right there. All right, so we need to. 204.8, I can do fractions now. 204.8. Yeah, that's as loud as it's gonna get right there.
Wait, it's actually started?
Yeah,
Oh.
all right, so.
Oh,
Is that
it's
signal
low.
okay?
All right, I'm hoping that, Amina, Amina, sorry, can you hear it? Sort of keep the sound in your head. All right. There we go. Now it stops. You can relax. All right, so first harmonic. Is that as loud as that?
That's it, that's it.
The lowest I can do here, and that's a higher pitch than what I was flashing around. That's because what's happening here when I swing this thing around, this end is obviously moving faster than this end. Because this is moving faster, the pressure, air pressure up here is less than the air pressure down here. And so it basically sucks up air through the tube. As the air gets sucked up through the tube, it hits the ridges and will start to vibrate. and then we can start getting the harmonics. To get the first harmonic, I have to swing it so slowly that there's not enough air pressure difference between the two to cause enough air to come up through it. So the first harmonic we actually cannot hear. Or, I nailed it perfectly. Second harmonic we should be able to hear. So, in your mind, picture what the second harmonic's going to sound like, or sorry, what it's going to look like, and I guess we don't need that, assuming that would come with a speaker. So the next harmonic, again, just like before, we add a half wave every time. We need to make sure we have an anti-note at the end. How many waves is that? Yes. We had a half wave before, we add a half wave every time. So this time L is equal to the wavelength, or solving for the wavelength is equal to L. L, we already measured that. So this is 0.83 meters. So this is our math problem. Instead of 1.66, we put in the new wavelength of 0.83. And the frequency for the second harmonic, so frequency for the first harmonic was 204.8 hertz. The second harmonic,
409.6.
it's just twice what we started with. Hopefully this will play louder. Four oh nine point six. Trust me, you can hear that. Hopefully you can hear that there's some similarity there. The question is, how close are we? So now let's get into constructive, destructive interference. We'll do a little side turn right here, just as what happens when you have two waves of different frequencies that are playing. This is in essence is how piano tuners, back when they still existed, piano tuners would tune pianos is they know what the frequency of the string is supposed to be, they pluck it, they play a tuning fork that is the right frequency, and then they listen for the differences between the two frequencies. Now, it might sound more of a challenge doing that, but there is an easy way to tell the difference. So if I have a wave that is like this, and I have another wave at a higher frequency, so these two waves, clearly different frequencies. Well, notice that there's a pattern that emerges here. That when this is peaking, this is somewhat peaking. We have constructive interference here. At this point right here, it's troughing. We're down below, and up here, we're still on the upside. They would do some canceling out. So we have destructive interference happening there. So when the two waves played together, we'd have this series of constructive, destructive interference. And this is what it sounds like. I'm gonna play 400 hertz, and I'm gonna play 401 hertz. I'm hoping you can all hear that. When it's the loudest, we have the most constructive interference. When it is the lowest, we have the most destructive interference. what you would end up with if they were really close to each other is a wave that starts out with a lot of constructive interference and then starts repeating. So this is when it fades out, and this is when it's the loudest. Now, the math to figure out what the frequency of that combination is, how often does it get really quiet, I generally advertise as the most sophisticated math that we will face. But don't psych yourself out yet. So I played 400 and 401, so I played 401 hertz, and I played 400 hertz. Here's the math. There we go, done. This is known as the beat frequency. So if the beat frequency is 1 hertz, what would be the period? What's the beat period? Besides the late 60s. I guess beat period would be the 50s. Apologies for that one. What would be the beat period? If you have frequency, how do you find period? Yes. Ethan? Were you about to say it?
Oh, no, I was looking through what I wrote down earlier.
Okay. As Brianna said, I don't know if you heard back there. I guess you're farthest away. Take the reciprocal. So the period is 1 over the frequency, so that would be 1 over 1. If you pull out a calculator to do this one, you need help. Units? Like you mean it. So let's find out if that gets quiet once a second. 1001, 1001, 1001. Now, if I'm 2 off, so if I play 400 and 402, what will be the beat frequency?
Can you repeat that? Sorry.
If I'm playing 400 hertz and 402 hertz, what would be the beat frequency?
2 hertz.
Yeah, and what would be the period?
Half a second.
0.5 seconds.
Okay, so it's going to sound a little bit trillier. So here's 400, 402. And the farther off I get, so let's now do 410. So if I do 410 and 400, the beat frequency
10.
and the beat period,
1/10 of a second.
yep. So the farther off we get, the more it gets to be more like a trill. I'm just going to do one more 430. That's 430 and 400. So those are 2 that are 30 hertz off. So now we have a way of actually coming up with some measure. This is our prediction. Oh, question?
When finding the beat frequency, can you just subtract the like big number minus small number, or do you have to like?
The big minus small. Yeah, that's the absolute value of whatever the difference is. Yeah, if I did 401 and 400 on this, if I did 400 and 399, it would sound the same. Well, the beat frequency would still be the same. It depends on how good your hearing is. Actually, let's check hearing for just a second here. This is 400. This is 401. Anybody catch the difference there? You said, uh-huh? And some people, I've had students who have much better tuned ears who can hear that difference. I cannot, but musicians tend to. I assume you play an instrument or you just gifted, okay. Well, I guess you could be, but they're not mutually exclusive. But, yeah, for the rest of us, we need to do the beat frequency in order to hear that if there's a difference between them. All right, so, any other questions before we test to see how close we get? There's a small little shrill there if you're listening for it. Without that. And so, and with it. If you're not listening for it, you may not necessarily hear it, but I do hear a small little trill. We could be 40 hertz off. Stop. Let's do the next harmonic, see what that gets us. Next harmonic's a little bit easier for me to play. The second harmonic, yeah, I have to get to a rhythm. The third harmonic is a little bit easier to maintain. All right, third harmonic. Picture in your head what it's going to look like when I draw my waves. There is L. How many waves is that? Yes. So my wavelength will be L divided by 1.5, which is 0.83 divided by 1.5, which is something. So 0.55, repeating. No?
Yeah, that's right.
Yeah. Meters. Now let's figure out the frequency that we should hear. Again, we're going back to the speed is equal to the frequency times the wavelength. I have 340, which is approximately the speed of sound in this room, times my frequency times 0.553 repeating. And we get a frequency of, it's going to be 6, 1, 4.4-ish. What is it?
0.82, 0.83.
Not 4, but 0.83 units. All right. So 6, 1, 4, 0.83. Nailed that. Now, part of the difficulty that I have in doing this is the fact that the material for the speaker and the material for this are different. The official term is the timbre or timbre. How's that supposed to be? I've heard it pronounced both ways. So the timbre or the timbre is different because the materials are different. There's a slight sort of, they can play the same note but still sound different just because of the materials. That's my excuse and I'm sticking with it. But hopefully it was close enough to give, again, a little bit more credence to some of the stuff I'm saying. And if not, then just trust that it's supposed to work. But it's a physics demonstration, so play your bets whether it actually works or not. Any questions? I'm gonna take a small little break here. And preferably not more than 5 minutes. There's certain things I want to get done when we're done, then either 2:20 or when I'm finished with what I want to cover, we'll call it stop at that point. But there's something I printed out before that I need to go grab. So I will pause this and hope to remember to turn it back on. All right, we're rolling. All right, so let's talk about the speed of, are there any questions? So let's talk about the speed of a wave. There's the one formula that we had that the speed is equal to the frequency times